So the next speaker is Sher Ali Penza with a talk on E-endomorphism of upper semigroup of bicyclic monoids. Please, up to you.
Good afternoon, everybody. And today my talk is on E-endomorphisms of the upper semigroup of the bicyclic monoid. Today we have seen already the definition of the bicyclic monoid. The bicyclic semigroup is a semigroup with the identity element generated by two elements P and Q, subject only to the condition PQ Q1, and the semigroup operation is determinate as follows. Okay. We define the following subset of the bicyclic semigroup. C plus is the subsemigroup of the bicyclic monoid. Yes, we already seen it. And previously, we described all monoid endomorphisms of the semigroup of our semigroup and the monoid endomorphism of C plus, which are restrictions of the homomorphism of the bicyclic monoid. In this presentation, we describe the semigroup of E-endomorphisms of the monoid C+. By E-endomorphisms, we understand the monoid endomorphism whose image is subset idempotence of the upper semigroup. On this slide, we see an example of E-idempotent. I'm sorry, we see the example of endomorphism of our monoid. The map tau defined by the following formula. Tau is monoid endomorphism of upper semigroup, and for any positive integer n and any element of the upper semigroup of the bicyclic monoid, you have this formula. And in this slide, we see the example of E-endomorphism. For any positive integer n map rho n, defined by the formula, is a monoid endomorphism, and moreover, rho n is an idempotent of the semigroup of endomorphism of our monoid. We denote by this symbol the semigroup of endomorphism of our monoid that generated by endomorphisms rho. And this semigroup of endomorphisms generated by endomorphisms rho is isomorphic to the semi-lattice of positive integer with operation maximum. We observe that the composition of E-endomorphisms of the semigroup C+ is again an E-endomorphism, because any homomorphic image of an idempotent is an idempotent. By this symbol, we denote the semigroup of endomorphism which consists of all monoid E-endomorphisms of the semigroup C+. By omega max, we denote the set omega with a semi-lattice operation. N times m equal maximum between n and m for any nm in omega. We extend the semi-lattice operation of omega max onto omega star. It's the union of non-negative integer and the symbol infinity. And infinity is not belong to omega in the following way. Okay. The set omega star we saw defined in semi-lattice operation. We denote by omega star max. It's obvious that the element infinity is the zero of omega star max. An endomorphism epsilon of the semi-lattice omega star max is called bounded if there exists an epsilon in omega such that the image of any element in omega star max by endomorphism epsilon less or equal n epsilon. It's obvious that the composition of any two bounded endomorphisms of the same lattice omega star max is bounded endomorphism. By this symbol, we denote the semigroup of all bounded endomorphisms of same lattice omega star max. And the main result is two theorems. Let alpha be a monoid endomorphism of the semigroup C+, then the following conditions are equivalent. First, alpha is an E-endomorphism. There exists a non-idempotent element of our semigroup such that the image of this element by endomorphism alpha is an idempotent of our monoid. And the image of all semigroup C plus by endomorphism alpha is finite subset of semigroup C plus. And the next theorem states that the semigroups of all bounded endomorphisms of similarities omega star max and the semigroup of all E endomorphisms are isomorphic. And it's all. Thank you for your attention.